Standard cosmological models encounter a severe mathematical wall when attempting to describe the extreme interior of a black hole. General relativity predicts its own demise at this center, yielding a singularity of infinite density where the equations of classical physics cease to function. Simultaneously, quantum mechanics requires strict information conservation. This principle is threatened by the formation of a singularity and the subsequent loss of data through Hawking radiation. The ultimate symptom of this theoretical conflict is the vacuum catastrophe, where the predicted energy density of empty space exceeds observed values by 120 orders of magnitude. The shared flaw across these paradoxes is the basic assumption of a continuous vacuum. Resolving these contradictions involves moving away from the smooth manifold and toward a discrete geometric model. The infinite fractal descent, or IFD framework, replaces the continuous manifold with a new underlying geometry. In this model, empty space is defined as a matrix of discrete spheres, densely packed and existing at a smaller subscale dimension. This comparison illustrates the shift. The classical continuous spacetime on the left is a featureless plane, while the IFD discrete matrix on the right consists of individual nested units. This nested hierarchy provides a dynamically sustained structural backing, allowing the matrix to participate in the physical behavior of matter across different scales. Replacing the continuous void with this discrete matrix establishes a physical scaffolding designed to prevent the emergence of mathematical infinities. The vacuum matrix is not static. Under gravitational stress, it transitions from an ordered, tame phase into a chaotic, elongated phase. During this phase, the vacuum generates Kakeya needle sets. These fractal structures maximize directional complexity within the smallest possible volumetric measure. To maintain local coherence, a self-tessellating Johnson solid called the gyrobiphostigium acts as a mechanical mediator. By adjusting its roof angle, the gyrobiphostigium absorbs the arithmetic jitter of subscale fluctuations, stabilizing the system into uniform metatile patterns. This process is managed within a 3D temporal framework, or T-space, which concurrently processes the arithmetic constraints of the past, the present metric, and the future search space. This makes the vacuum a self-correcting mechanical code, engineered to isolate and absorb mathematical instability before it can trigger a systemic collapse. These matrix mechanics suggest a different interpretation of the event horizon than the standard point of no return. In this diagram, the event horizon is a structural phase transition. The dashed boundary marks where sparse, macroscale matter yields to the dense central cluster. This behaves like the liquid-vapor critical point of a Bose fluid, as larger structures break down. As matter collapses, the vacuum exerts a topological drag known as geometric friction, which we map to the diffusivity parameters of Schramm-Loener evolution. This friction dictates a spatial compression equation, where density eventually hits a rigid sphere packing limit, physically halting the collapse. Consequently, black holes are viewed as hyperdense, dynamically sustained spacetime configurations, where internal friction prevents the formation of a singularity. This structural density limit changes the nature of the information paradox, starting with a redefinition of Hawking radiation. Rather than thermal evaporation, Hawking radiation is interpreted as coherence leakage, the mechanical displacement of the subscale matrix. As macroscopic matter grinds against the extreme density of the matrix at the event horizon, it bleeds kinetic energy into the environment. The quantum information of that matter is re-encoded into murmuration patterns within the spheres of the matrix. Unitarity is preserved. The system translates the quantum information and locks it into the murmuration patterns of a smaller structural dimension. If the universe operates as a discrete geometric matrix, a specific mechanism must prevent it from falling into infinite symmetry or informational heat death. This is the Einstein hat tile. In the IFD framework, this 13-sided outline serves as a topological cutoff mechanism. The inherent aperiodicity of this geometry creates a geodesic trap. While the tiles fit together cleanly, they mathematically forbid the formation of a repeating infinite grid. This trap physically prevents arithmetic failure, remainders, from compounding, stopping systemic singularities before they can form. This structural aperiodicity safeguards the cosmos, forcing energy remainders into oscillatory mass spectrums rather than catastrophic infinities. These subscale geometric rules have direct consequences for macroscopic relativistic mechanics. Once matter crosses the phase threshold, it follows a modified polytropic equation of state, behaving as a stiff relativistic fluid. This fluid is characterized by an internal structural backpressure that resists further compression. Numerical solutions to the TOV equation for this fluid show the speed of sound approaching but never exceeding the speed of light. This stiff fluid model ensures that even within the extreme interior of a black hole, strict relativistic causality is maintained. These internal fluid mechanics also provide a framework for understanding the accelerating expansion of the universe. In the vast voids of the cosmic web, where macroscopic matter is absent, the underlying matrix is at its most influential. Within these voids, the subscale fluid exerts its outward thermodynamic backpressure entirely unimpeded. When we map this equation of state to the macroscopic scale, the outward topological drag of the vacuum aligns with the observed expansion of the universe. Mapping the internal friction of the matrix to the vacuum's topological drag aligns the model's predictions with the observed properties of the cosmological constant. By treating spacetime as a mechanically active, fractal hierarchy, this framework resolves infinite singularities, preserves essential quantum information, and physically explains dark energy.